All right, this is chapter 1, section 4, combination of functions. We are going to be combining functions using basic arithmetic operations, addition, subtraction, multiplication, and division. We're going to determine the domain of the quotient of two functions, so when we divide them, and we're going to be combining functions using what are called compositions. All right, so first off, there's some notation here that we need to be a little bit familiar with. The sum of two functions here can be written this way, f plus g of x. What that really means is we just take the two functions and we add them together and we get a new function. The difference of two functions written f minus g of x is again, same idea, two functions, we subtract them. The product f times g of x is just multiplying two functions together. And then finally the quotient, a little more complicated because we have a fraction here, but we're essentially dividing two functions or putting them in a ratio, f over g of x. So let's go ahead and find the sum and difference of these two functions. So first one I'm going to do over here, I will do the sum of the functions. So f plus g of x. So when we're adding, it doesn't really matter the order. If this was subtraction, it would be important, but I am going to do it in the order that it's written here. So that's just going to be 2x plus 1 plus this other function, x squared plus 2x plus 1. With adding, we're just going to be combining like terms. So we're going to get x squared plus 4x plus 2. And so our answer here is going to be this function, the sum of these two functions, f and g. All right, we'll do the next one here, the difference. So taking our two functions and we're subtracting them. Now with subtraction, it does matter the order that we do it. They would differ by a factor of -1 if we do our subtraction in the wrong order, so that's important that we do it in the right order. We're going to take our initial function f, and we're going to subtract g. I'm going to go ahead and put it in these parentheses just to make sure I remember to subtract the whole thing. And I'm going to distribute that. Negative. Right, so this is f minus g of x. Kind of left that off there, but that's okay. And now it's just a matter of combining like terms. I have plus 2x minus 2x. Those will go away. I have plus 1 and minus 1. They'll also go away, which actually just leaves me with negative x squared. So that's actually a pretty nice answer for our difference of those two functions. All right, we'll clear those away, and we'll look at some quotients and products. So here we have two functions, and we are going to find the product and the quotient of these two functions. So first, f times g of x. That just means we're going to take these and multiply them together. So we're doing 6x times the other function. Now, you could imagine this multiplication could get complicated if we had multiple terms and had to distribute and everything, but this should be just pretty easy. Just going to be distributing 6x there. So 6x times 2x squared is 12x to the third. 6x times that is going to be negative 24x. So there we go. Now the quotient, it says g over f. So g on top, f on bottom of x. So that's going to be 2x squared minus 4x all over 6x. Now, if we were talking about the domain of a function like this, we would want to make sure we don't include any values that would have our denominator equal to 0. So x equals 0 would be excluded from our domain. X cannot be equal to 0. But we can simplify this out. Both we can simplify out in x, and we could find a common factor for all these numbers, right? All these numbers are also divisible by 2. So if we do that, this divided by 2 is going to be just 1. And then if we divide through, let's do this. Let's factor the top. The top will factor as 2x times x minus 2 over. And then 6x, I could think about that as being 2x times 3, right? So that lets us cancel out our 2x and our 2x, and we're left with our simplified version of this function, which would be x minus 2 over 3. Now, even though this is not a problem, x could totally be 0 in this function, it cannot be 0 for this quotient, because based on the original function, before we did simplifying out that x, 0 caused a problem. So it still cannot be included in this domain. Okay. Same idea here. Let's look at this. We're going to specifically only focus on the domain here. So remember, the domain for quotients are really all about anything that makes the denominator equal to 0. So we're doing f over g first. So f over g of x. Again, for any function like this, for any quotient function, the part that really matters is the denominator. The denominator cannot be equal to 0. So when I write this one out, it doesn't even frankly matter what's on top. For all we care, anything can be up there. But in this case, it's x plus 7. It's what would make the denominator equal to 0. These have to be excluded from our domain. So this is a quadratic that we can factor just by greatest common factor. We both have an x, so I factor out an x. And then we have our two solutions. So this factor would tell us that x equals 0 would be a problem, and this one would tell us that x equals 8 would be a problem. So the two excluded values from our domain here would be that x cannot be equal to 0 or 8. Very, very similar. Again, we don't care about the top, we only care about the bottom. So if we reverse this quotient and we do g on top, again, all we really care about is the bottom. So we have x. That's all we care about in this case. So pretty simple on this one. We're going to see that we know it cannot be equal to -7. No factoring necessary. -7 is the number that would cause this to be 0. It's just a simple linear factor. We don't really care what's up here, but this is what would be on this case. So it's our domain. X cannot be equal to -7. All right, now the other way that we can put two functions together is as a composition. A composition is formed when one function is put into another function as an input. The result is called a composition. The order of the composition is important. So if you have two functions, f and g, whether you're putting f into g or g into f, you're likely to get different results. So the order matters. All right, so let's go ahead and look at this. So we have two functions, f and g, and we're going to compose them. Notice how things are written here. Seeing how g is on the inside right there, that means that we're going to be putting g inside of f. Whereas here, now f is on the inside, so we're going to be putting f inside of g. They're going to be similar, but different. So it's important to make note of which way you're doing this. So I'm going to go ahead and rewrite this. So instead of f of g of x, I'm going to write this as f of, and then I'll use the function rule of g of x. So I'll say f of x squared plus 7. That helps me think about it. So instead of putting in the whole function, I'm just putting in the rule of the function for x. So this is going to be 3 times x minus 1. And again, x was our new function. We're putting g of x inside right here. So now obviously we can do a little bit of simplifying there. We can distribute, and we'll also be combining like terms. So this is going to be 3x squared plus 21 minus 1, and then combining like terms there at the end, 3x squared plus 20. So this is my f of g of x. This is my composition function for the first one. Now, like I said, the other one is going to be a little bit different, not exactly the same, but likely similar. So this time we're putting f on the inside. So I'm writing this as g of 3x minus 1. 3x minus 1 being the function for f of x. So now my g function is x squared plus 7. But g is taking the input of 3x minus 1 this time. So then I need to go ahead and multiply that out. That would be 9x squared minus 6x plus 1 plus 7. So similar but different. It's still a quadratic, but we're getting a different overall answer here. So that's what I mean by it's important about the order of our composition. All right, so that's going to be 9x squared minus 6x plus 8. Yep, and that is our composition the other way. Similar functions, but not the same. So the order was important here. Let's clear those. Okay. The other way that we can write compositions, so I like this way. I think it's very clear about what's going on the inside here. We're putting g inside of f, but this same composition can be written this way. We're reading it f of g of x, so we're using the function f, inputting the function g. This is a little more confusing personally, but it's another way that it's written. Likewise, if we want to say it the other way, g of f of x, f going inside of g, we can write that g of f of x. Little o there stands for the composition. But again, this means that we're starting with the function g, we're putting in the function f. Just another way to write compositions. All right, so some more details. You can compose a function with itself, so we can take f and put it inside of itself. So f of x. So we'll do that with this function right here. So we're taking the function f, and remember, we're putting in f again. So we're really doing f of 1 minus x over 3. So I'm going to start with my function f. So it's 1 minus x, which is where we take our input. My input is this, 1 minus x over 3. And from here, there's just a little simplifying to do. 1 can be thought of as 3 over 3. So I can kind of 3 over 3 minus 1 over x over 3, kind of get things rolling that way. So 3 minus 1 is negative 2. We're distributing that negative, so it's a negative 1 plus an x. So 3 minus 1, that's where I would actually get that as a positive 1. That was my mistake. And then plus x over 3 over 3. This is a complex fraction. Ideally, we would like to go ahead and get rid of that. So I can multiply the top and the bottom by 3 to get rid of that right there. And so that's what I would do. Multiply the top of my fraction, the bottom of my fraction by 3, so that I can end up with 2 plus x over 9. So that was a composition of a function with itself, right? Use just one function to do that. A little bit messy, but it can be done. Okay, and then I'm just going to run through a few more examples of compositions here. So we're going to do it both ways, G on the inside and F on the inside. Start with an easy one, and we'll kind of work our way up from that. So I'm going to do this first. This will be my first one. So I'm doing f of g of x. So f of x minus 3 over 2. Okay, so my function f is 2x plus 3. And I'm putting in x minus 3 over 2. All right, so actually I'm seeing a little bit of simplifying here. These 2's will cancel. So I end up with simply x minus 3 plus 3. Minus 3 plus 3, this ends up being x. So my first composition, f of g of x, is just x. Simplifies quite nicely. That would signify something special to us if we remember about inverse functions, but that's for next chapter as well. So next I'm going to go the other way. I'll do f on the inside. So I'm doing g of f of x, which is 2x plus 3. All right, so starting with my g of x. When I do these compositions, I write the outer function, but I give myself a big open parentheses anywhere the x would be. And so in there is where I put the function rule for whatever's going on the inside. All right, well, there's nothing really to do with these parentheses, but the plus 3 and the minus 3 do cancel out. So we end up with 2x over 2. Those cancel out, and we end up with just x again. And this is g of f of x. So in this case, these both simplify to the same thing, and it's just x, which actually means that these are what are considered to be inverse functions. Again, we'll get way more into that in the next section. All right, and we're going to do a couple more of these, 2 more, I believe. All right, here we go. We have f of x is 1 over x, and then g of x is the square root of x minus 5. So I'm going to first do f of g of x, which means I'm doing f of g of x, which is root x minus 5. So 1 over x, which is root x minus 5. Now, not a lot to do here. We don't like having square roots in the denominator, so generally we would go ahead and rationalize that. So we would multiply by root x minus 5 on the top and bottom, just to get this radical out of the denominator. It isn't going to do a lot for us in terms of simplifying, though. Actually, the function looks a bit more complicated like this, but it doesn't have any radicals in the denominator anymore. So that would be our composition this time of f of g of x. Okay, and then go ahead and go the other direction, g of f of x. So that means I'm doing g of 1 over x, which is the square root of x minus 5, x being 1 over x. Not a lot I can do here. Again, if I kind of, there's really nothing to do here. I can actually just kind of leave it exactly like that. So this is g of f of x. It's just going to be the square root of 1 over x minus 5. That's it. Sometimes we can do a lot, like those previous examples. Sometimes we can't do much, like that. Okay, and the last page here, we'll go ahead and look at these. All right, we have f of x is x squared minus 9, and then g of x is the square root of 9 minus x squared. Okay, we'll go ahead and do the first composition here, so we're doing f of g of x, which is root 9 minus x squared. All right, f of x is x squared minus 9, and what we're putting in there is square root of 9 minus x squared. Well, lucky for us, the squaring and the square root cancels out really nicely, so we end up with just 9 minus x squared minus 9. 9's actually cancel out, 9 minus 9 being 0, so we end up with just negative x squared. So this simplifies a lot for our first one. But remember what we were saying before about how the domain of this function, even though technically right here we could put any number we want into it, but at this stage right here, before simplifying, because of this radical, radicals cause a lot of restrictions to our domain. So we would want to look at our function right here and make sure there weren't any x's that would be restricted. So just offhand, the number 5 would cause a problem because 9 minus 5 squared, that's going to be a negative 16. Square root of a negative is not going to give us a real number, so we wouldn't want to include that in our domain. All right, second one here, g of f of x. So we're doing g of f of x, which is x squared minus 9. So I'm starting with my g function. I'm doing 9 minus x squared. Okay, this one's not going to be as nice, but let's see how it goes. X squared minus 9. Because squaring that is going to give us a larger polynomial, so I don't even care what that says. Okay, so here we go. That's going to be 9 minus, get x to the 4th minus 18x plus x squared, 18x squared plus 81. And we are subtracting that, so we want to go ahead and distribute that. That's 9 minus x to the 4th plus 18x, and then minus 81, 18x squared. I keep wanting to write that middle term incorrectly. And the 9 and the 81 can't actually go together, so otherwise not much else can be done with this. So let's see, 9 minus 81, that's going to be negative 72. And that is g of f of x. I'm mixing up my notation here just to show it in both ways. Again, my preference is like this. It makes a lot more sense to me, but this is fine too. All right. Hopefully that helps. Try out the homework on this page and send me an email or message on Google Classroom if you're having trouble. Thanks.